Welcome to this video on ISTQB CTAI. This overview covers fundamental concepts in artificial intelligence relevant to software testing. We are now moving into Chapter 3, which explores machine learning and its application in AI systems.
ML algorithms are categorized into supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, algorithms train models using labeled data, where each set of inputs has a corresponding output label, for example, images labeled as dog or cat. The model learns to map inputs to outputs by identifying patterns in the training data. Supervised learning is typically divided into classification. This involves assigning inputs to predefined classes, such as classifying emails as spam or not, or image recognition in images. And ML regression, this involves predicting continuous numerical values, such as estimating a person's age based on lifestyle data or forecasting stock prices. Note that the term ML regression, when used in the context of ML, differs from its use in other ISTQB syllabi, where regression describes the problem of software modifications causing change-related defects. In unsupervised learning, the algorithm trains models using unlabeled data, inferring patterns or structures without explicit output labels. The model groups similar inputs together based on shared features. Unsupervised learning is typically categorized into clustering. This involves grouping data points based on similarities, such as segmenting customers into different groups for targeted marketing. And association. This involves identifying relationships or dependencies among data attributes, such as finding patterns in customer purchasing behavior to recommend products. In reinforcement learning, the AI-based system, an intelligent agent, learns by interacting with its environment. The agent receives positive feedback, rewards, or negative feedback, penalties, based on the outcome of its actions, enabling it to learn from experience rather than from a dataset. Challenges in reinforcement learning include setting up the environment, designing the reward function, and selecting the best strategy to meet the desired goal. Applications include robotics, autonomous vehicles, and adaptive systems, like chatbots. Each ML approach addresses different types of problems, with the choice depending on the nature of the available data and the specific task at hand. The activities in the ML workflow, shown in Figure 1, are understand the objectives. The purpose of the ML model is understood and agreed to by the stakeholders to verify alignment with business priorities. Acceptance criteria are defined for the developed model. Select a framework. A suitable ML development framework is selected based on the objectives, acceptance criteria, and business priorities. Select and build the algorithm. An ML algorithm is selected based on various factors, including the objectives, acceptance criteria, and the available data. The algorithm may be manually coded, but it is often retrieved from a software library. The algorithm is then compiled if required. Prepare and test data. Data preparation comprises data acquisition, data pre-processing, and feature engineering. Exploratory data analysis, EDA, may be performed alongside these activities. The data used by the algorithm and model are based on the objectives and are utilized by all activities in the model generation and test box shown. The data used to train, evaluate, tune, and test the model must be representative of the data that will be used by the model operationally. Testing of the data and any automated data preparation steps is performed. Train the model. The selected ML algorithm uses training data to train the model. Parameters defining the model structure, say the number of layers of a neural network or the depth of a decision tree, are passed to the algorithm. These parameters are known as model hyperparameters. Parameters that control the training, say the number of iterations to use when training a neural network, are also passed to the algorithm. These parameters are known as algorithm hyperparameters. Evaluate the model. The model is evaluated against the agreed ML functional performance metrics, using the validation dataset, and the results are used to improve the model in the tune the model activity. In practice, several models are typically created and trained using different algorithms, say random forests, SVM, and neural networks, and various training datasets, and the best combination is chosen based on the evaluation results. The results from the evaluation are used to adjust the model hyperparameters and the algorithm hyperparameters. The model is then retrained with these adjusted settings to improve its ML functional performance. The three activities of training, evaluation, and tuning comprise model generation, as shown on Figure 1. Test the model. Once an acceptable model has been generated by the model generation activities, it is tested using an independent test dataset to verify that the agreed ML functional performance criteria are met. The test results are also compared with those from the evaluation. If the performance of the model with independent test data is significantly lower than during evaluation, it may be necessary to return to the model generation activities, or even to the prepare and test data activity to train a new model. In addition to ML functional performance tests, non-functional tests, such as for the time to provide a prediction, may also be performed. Typically, testing in this activity is performed by data engineers or scientists. However, testers with sufficient knowledge of the domain and access to the relevant resources can also perform this testing. Deploy the model. Once model generation and test is complete, the tuned model is typically re-engineered for deployment along with its data pipeline. This is generally achieved through the ML development framework. Target platforms might include embedded systems and the cloud, where the model can be accessed via a web API. The re-engineered deployed model is tested to verify it still meets its acceptance criteria. Use the model. Once deployed, the model is typically integrated into a larger operational AI-based system. Models may perform scheduled batch predictions at set time intervals or run in real time upon request. While the model is being used, its situation may evolve, and the model may drift away from its intended performance. To verify that any drift is identified and managed, the operational model is regularly evaluated against its acceptance criteria. It may be deemed necessary to create a new model by retraining with new data, retraining with new hyperparameters, or both. The latest model may then be compared to the existing model using a form of A/B testing. The ML workflow shown in Figure 1 is a logical sequence. However, in practice, the workflow is applied iteratively, with steps repeated. The steps shown in Figure 1 do not include the integration of the ML model with the non-ML parts of the overall system. Typically, ML models cannot be deployed in isolation and must be integrated with non-ML components. For example, in vision applications, a data pipeline is used to clean and modify data before submitting it to the ML model. When the model is part of a large system, it must be integrated into this system before deployment. In this case, integration, system, and acceptance test levels may be performed. Training a new AI model from scratch is both costly and time-consuming. To address this, a common solution is fine-tuning, which involves taking a pre-trained neural network and adapting it to perform a new, different task. One of the key benefits is that it requires much less training data and training effort compared to building a model from scratch. The pre-trained model is fine-tuned by performing additional training with data specific to the new task. The tuning can be applied to the entire neural network, only to specific layers, typically near the output end of the neural network, or to additional layers. After training, the model's ML functional performance is evaluated, and based on these results, further fine-tuning may be performed until the model meets the necessary acceptance criteria. Fine-tuning success depends on the similarity between the original and new tasks. Small differences can lead to highly effective fine-tuning. For example, adapting a cat breed image classifier to identify dog breeds is likely to work well. However, adapting it for spoken accents is less effective due to the larger difference. Similarly, fine-tuning an LLM for ISTQB-defined boundary value analysis requires a small change for the LLM and is readily achievable with good training data. An alternative to fine-tuning is retrieval augmented generation, or RAG, which involves providing data sources to the LLM that are specific to the required task. These data sources are transformed into a searchable format that allows them to be compared to the subject of the prompt. Once relevant documents are identified, these are incorporated into an enhanced prompt, which is passed to the LLM. As more pertinent information is now provided to the LLM, its corresponding response is likely to be more precise. With RAG, no change is made to the pre-trained model. A pre-trained model can use RAG, fine-tuning, or both together to enhance performance. Typically, any biases or vulnerabilities in the pre-trained model will carry over to the new model, so testing is necessary to confirm that it performs reliably and fairly in the new task. Activities in data preparation. Data preparation supports the achievement of the quality and suitability of data for model training. It involves several key activities. Data acquisition. Identifying relevant data types, for example, numerical, categorical, images, text. Gathering data from diverse sources, such as databases, APIs, or real-time sensors. Labeling data for supervised learning tasks, verifying accuracy and consistency. The acquired data can take various forms, including numerical, categorical, image, tabular, text, time series, sensor, geospatial, video, and audio. Data pre-processing. Cleaning data, including removing defects, duplicates, and outliers to verify data accuracy and consistency. Imputing missing values using techniques like mean, median, or mode to maintain data completeness. Anonymizing or removing personal information to protect privacy and comply with regulations. Transforming data formats, scaling, and normalizing to achieve consistency. Augmenting data to increase sample size, incorporating adversarial examples to enhance robustness against adversarial attacks, and generating synthetic data. Sampling subsets to reduce training times and computational costs. Feature engineering. Selecting relevant features based on their contribution to ML model performance. Extracting a subset of informative and non-redundant features from existing features to reduce training times and computational costs. In parallel to these data preparation activities, exploratory data analysis, or EDA, is also typically carried out to provide insights into the data. This includes discovering trends, patterns, and anomalies in the data, visualizing data using plots and charts for better understanding. Preparing training data is typically an iterative process, often performed manually, and individual data preparation activities may be reordered or omitted based on specific project requirements. The operational data should match the characteristics of the training data, for example, data distributions and feature ranges, so that the model performs as expected in production. However, the preparation steps themselves may be adjusted for production efficiency and scalability. Training, validation, and test datasets. Logically, 3 sets of equivalent data, for example, randomly selected from a single representative dataset, are required to develop an ML model. A training dataset is used to train the model. A validation dataset is used for evaluating and subsequently tuning the model. A test dataset, also known as the holdout dataset, is used to test the tuned model. If an abundance of suitable data is available, the amount of data used in the ML workflow for training, evaluation, and testing typically depends on the following factors: the expected complexity of the model, the algorithm used to train the model, the availability of resources such as RAM, disk space, computing power, network bandwidth, and the available time, the desired confidence in the resultant model. When data is limited, a 3-way split, train, validation, and test, can result in insufficient data for effective model training, thereby increasing the risk of underfitting. To address this, a common strategy is to set aside a small, final holdout test set, if feasible. The remaining data, the combined training and validation pool, is then used for techniques like k-fold cross-validation, where k is a user-specified integer, commonly 5 or 10. In k-fold cross-validation, this data is divided into k-folds. For each fold, the model is trained on k-1 folds and validated on the held-out fold. This process is repeated k times, with each fold serving as the validation set once. This allows for robust hyperparameter tuning and ML functional performance estimation. Data is typically randomly assigned to folds, often using stratified sampling to make each fold representative, especially with imbalanced data or small datasets. The performance metrics from each fold's validation are then averaged to provide a more reliable estimate of the model's generalization ability. After identifying the optimal hyperparameters through cross-validation, a final model is typically trained on the entire training and validation pool, all data except the holdout test set, using these hyperparameters. This final model is then evaluated once on the holdout test set for a final unbiased performance assessment. If a holdout test set is not feasible due to extreme data scarcity, the average cross-validation performance is optimistically biased and cannot serve as an unbiased estimate. Logically, 3 sets of equivalent data, for example, randomly selected from a single representative dataset, are required to develop an ML model. A training dataset is used to train the model. A validation dataset is used for evaluating and subsequently tuning the model. A test dataset, also known as the holdout dataset, is used to test the tuned model. If an abundance of suitable data is available, the amount of data used in the ML workflow for training, evaluation, and testing typically depends on the following factors: the expected complexity of the model, the algorithm used to train the model, the availability of resources such as RAM, disk space, computing power, network bandwidth, and the available time, the desired confidence in the resultant model. When data is limited, a 3-way split, train, validation, and test, can result in insufficient data for effective model training, thereby increasing the risk of underfitting. To address this, a common strategy is to set aside a small, final holdout test set, if feasible. The remaining data, the combined training and validation pool, is then used for techniques like k-fold cross-validation, where k is a user-specified integer, commonly 5 or 10. In k-fold cross-validation, this data is divided into k folds. For each fold, the model is trained on k-1 folds and validated on the held-out fold. This process is repeated k times, with each fold serving as the validation set once. This allows for robust hyperparameter tuning and ML functional performance estimation. Data is typically randomly assigned to folds, often using stratified sampling, to make each fold representative, especially with imbalanced data or small datasets. The performance metrics from each fold's validation are then averaged to provide a more reliable estimate of the model's generalization ability. After identifying the optimal hyperparameters through cross-validation, a final model is typically trained on the entire training and validation pool, all data except the holdout test set, using these hyperparameters. Moving on, this final model is then evaluated once on the holdout test set for a final unbiased performance assessment. If a holdout test set is not feasible due to extreme data scarcity, the average cross-validation performance is optimistically biased and cannot serve as an unbiased estimate. Calculation of machine learning functional performance metrics. In a classification problem, a model will rarely predict the results correctly all the time, partly due to the probabilistic nature of ML models and data noise. For any such problem, a confusion matrix can be created with the following possibilities. Note that the confusion matrix shown in Figure 2 may be presented differently, e.g. predicted and actual swapped, but it will always yield values for the 4 possible situations of true positive, TP, true negative, TN, false positive, FP, and false negative, FN. Based on the confusion matrix, the following metrics are defined. Accuracy equals TP plus TN divided by TP plus TN plus FP plus FN times 100%. Accuracy measures the percentage of all correct classifications. Precision equals TP divided by TP plus FP times 100%. Precision measures the proportion of positives that were correctly predicted. It is a measure of how sure one can be about positive predictions. Recall equals TP divided by TP plus FN times 100%. Recall, also known as sensitivity, measures the proportion of actual positives that are correctly predicted. It is a measure of how confident one can be that no positives will be missed. F1 score equals 2 times precision times recall divided by precision plus recall. F1 score is calculated as the harmonic mean of precision and recall, with values ranging from 0 to 100. A score close to 100 means the model achieves both high precision and high recall, indicating that classification errors, false positives and false negatives, have minimal impact. Conversely, a low F1 score indicates the model struggles to accurately identify positives, either missing true cases or generating many false alarms. Artificial neural networks were initially designed to mimic the functioning of the human brain, which can be thought of as a network of interconnected biological neurons. The single-layer perceptron is one of the earliest examples of implementing an artificial neural network, comprising just one layer. It can be used for supervised learning of binary classifiers for linearly separable problems, which determine whether an input belongs to a specific class or not. For example, a perceptron can distinguish between emails that are spam and those that are not spam by learning to separate the features of the two categories with a straight line in the input space. Most current neural networks are considered to be deep neural networks because they comprise several layers. Fully connected networks can be considered as multi-layer perceptrons. A deep neural network is typically described as comprising three main types of layers. The input layer receives inputs, for example, pixel values from a camera. The output layer provides results to the outside world. This might, for example, be a value indicating the likelihood that the input image is of a cat. Between the input and output layers are hidden layers, composed of artificial neurons, also known as nodes. In many common architectures, such as fully connected networks, the neurons in one layer are connected to each of the neurons in the next layer, and there may be different numbers of neurons in each successive layer. The neurons perform computations and pass information across the network from the input neurons to the output neurons, gradually transforming the input data into increasingly abstract representations until reaching the output. The computation performed by each neuron, after those in the input layer, generates what is known as the activation value. This value is calculated by first computing a weighted sum of the activation values from all connected neurons in the previous layer, where each such connection has its own independent weight, and adding the neuron's individual bias. This sum is then passed through a nonlinear formula called the activation function. Using different activation functions yields different activation values. The weights connecting neurons and each neuron's bias value are typically initialized to small random values, biases sometimes to 0, at the start of training. The training data is passed through the network, with each neuron running the activation function to generate an output ultimately. The generated output is then compared with the known correct result. The resulting error, or loss, which quantifies this difference, is then fed back through the network to adjust the values of the weights and biases, thereby minimizing this difference. As more training data is fed through the network, each pass through the training dataset is called an epoch, the weights and bias values are gradually adjusted as the network learns. After some time, ideally, the output produced is considered good enough to end training. Coverage measures for neural networks, structural coverage metrics, have emerged to assess how thoroughly test inputs exercise a model's internal mechanisms. As neural networks do not follow explicitly coded paths, but their behavior is dictated by learned weights, bias values, and activations, this creates a need for specialized coverage measures to evaluate the extent to which different parts of the network have been activated under test conditions. Typical approaches include neuron coverage, measures the proportion of neurons in the network where their output exceeds a specified threshold during testing. K multi-section neuron coverage. The possible output range of each neuron is divided into K sections. KMNC is the proportion of these sections activated during testing. Neuron boundary coverage measures the proportion of neurons in the network where their output either exceeds the maximum achieved in training or is less than the minimum achieved in training during testing. These coverage metrics can be helpful in AI testing, primarily by revealing areas of the model that remain untested, which may potentially hide defects or unlearned behaviors. For example, if certain neurons or layers never activate during testing, the model's performance in related decision boundaries might be questionable. Such insights help testers design additional test inputs or test conditions to exercise underexplored parts of the network. At present, commercial tools supporting these specific coverage measures are limited. However, structural coverage alone does not guarantee that a neural network will generalize well or handle real-world variations. Neural networks can learn spurious correlations, leading to correct activations for incorrect reasons. Consequently, testers should also use other test techniques,